Good morning, everyone, and welcome to the Hydrogen and Fuel Cells Europe Technical Forum here at the Hannover Messe 2023. Today we have a very interesting topic for you. We'll be talking about solid oxide fuel cells with Professor Anke Hagen. Please join me on stage. Thank you.
Thank you.
Take it away.
Yes, hello everybody. It is my great pleasure to present to you the NewSOC project. Solid oxide technology can operate in many modes. They can be used as a fuel cell, and they can also be used as an electrolyzer. And in addition, they can run in a reversible mode, switching between the two. And that's actually a unique feature of the solid oxide as compared to PEM cells or alkaline technology. And this flexibility is one of the reasons why we believe that solid oxide technology will play a key role and will be an enabling technology in the future energy systems where we base ourselves on renewable energy sources. It is very well suited for sector coupling that will be required in such systems between electricity, heat and gas. And in that way we believe they can play a key role and can be used in several sectors, like in the power production sector, in the Power 2X application, in regard to use of biogas, and also for balancing intermittent energy supply from renewable sources. Solid oxide technology is being commercialized, and you see a few examples here at this exhibition. And while this is the case, we are now already working at the next generation to deliver improved components, cells and stacks for solid oxide technology. In our specific NewSOC project, we had set out 25% targets to improve the performance as compared to state-of-the-art, to increase the cycling stability, to reduce costs, and also to reduce the use of toxic materials, both in the manufacturing and also in the device. The project was financed by the European Commission, specifically under the Fuel Cells and Hydrogen Second Joint Undertaking, which is now the Clean Hydrogen Undertaking, which is a public-private partnership to move forward hydrogen technologies. And we are now in the final project phase that will end by the middle of this year. In this project, we joined forces between 16 partners. We were 11 partners from academia, from universities and from research centers, and we were 5 partners from, these are actually the major players, industrial players in Europe. And as you see on the map, we were also quite well distributed from north to south, east, west in Europe. In the project, we pursued 12 concepts. That means we tried 12 different ideas to improve current technology and to develop a next generation. And these 12 concepts related to cell and stack components can be grouped into 3 subtopics. And one of them is structural optimization and innovative architecture. And here we relied on state-of-the-art materials that are used in the cells and stacks that that industry is commercializing, because we believed there is still a big potential to improve those. In the second group, we developed alternative materials, because we already see that the materials we are using now, they have some challenges, and to overcome them, we worked on alternative materials. And finally, we worked on alternative manufacturing. We know that to be cost competitive and to be environmentally acceptable, we need to reduce costs, use of toxic materials, and this was, among others, a target in this group of innovative manufacturing development. All that what we improved was not stopped at the university or laboratory level. We integrated all elements into industrial platforms, either in cells or in stacks that were provided by the partners in the project. And in that way, we validated the improvements that we had achieved. And we made use of these 5 partners from the project. They all stand for planar technology, and they actually stand for the major concepts that we know in solid oxide technology. That is on top the fuel electrode supported configuration, in the middle the electrolyte supported configuration, and on the bottom the metal supported configuration. And for each configuration we had industry partners. We indeed achieved to improve electrode and stack performance using state-of-the-art materials. Now, when you are in the field of this solid oxide technology, you know that commercial players are using nickel YZ, nickel with yttria zirconia composite fuel electrodes. We are using cobaltite ferrite-based air electrodes. These are perovskite structures. And we are using barrier layers made of cerium gadolinium oxide. In the project, we succeeded to improve those by improving the structure within the electrodes. That was achieved by a circle of modeling, electrochemical and microstructural characterization. In that way, we actually could harvest a 25% improvement by improving the structure of state-of-the-art materials. We integrated these developments in commercial cells and stacks provided by Solidera, formerly Solid Power, and Elcogen, and validated these improvements on this relevant platform. We also know that state-of-the-art cells have some challenges regarding tolerance. For example, tolerance towards sulfur impurities, or carbon tolerance when we are working with carbon-containing gases, such as biogas when we are working in fuel cell mode, or CO2 when we are doing CO2 or co-electrolysis in electrolyzer mode. In addition, when the fuel electrode is exposed to oxidizing conditions, we can have a fatal failure due to redox. We try to improve and solve these challenges with new materials. For example, for sulfur tolerance, we could show that new fuel electrodes that are not based on nickel YZ or nickel ZgO, but based on titanates, more specifically lanthanum, strontium, iron, nickel titanates, we can improve the sulfur tolerance. Furthermore, we could improve the carbon tolerance by using bi- or trimetallic nickel ZgO, cerium gadolinium oxide fuel electrodes. We also succeeded to reach a very high stability towards oxidizing conditions by using chromite-based fuel electrodes. And finally, we also could demonstrate improvements in reversible operation between fuel cell and electrolyzer mode by using fuel electrodes that either contained titanate-based structures or by trimetallic infiltrated nickel ZgO fuel electrodes. So by introducing new elements and new materials, we were able to solve some of the challenges of state-of-the-art nickel YZ fuel electrodes. As you see, all these elements are on one electrode side, the fuel electrode, and they were integrated into 2 platforms. One was the electrolyte-supported platform, and one we also investigated on metal-supported cells that we made in-house. And here we could actually also transfer the lab results to industrial cells. And finally, reduction of toxic materials is, of course, a long-term issue. We know that cobalt is on the list of critical raw materials, and cobalt is unfortunately an ingredient in the most active air electrodes that we are using today. In the project, one of our partners succeeded to make ferrite air electrodes by both using new materials but also new interfacing structuring. We were also able to substitute partly the cobalt in a protective coating that we are applying to protect the interconnects in a stack from corrosion. It was not possible to completely substitute, but partially. And another development showed that we were able to deposit sealants without using toxic solvents. Also, all these developments were integrated both into electrolyte-supported or fuel electrode-supported configurations and validated at that level. In that way, the project was quite successful to achieve the goals that we had set ourselves initially. Now, and what now? The project is at its final phase. Here you see actually an illustration of the 12 concepts that are targeting electrodes or stack components. We achieved these improvements, and we used scalable methods or methods that are already established for the production of solid oxide technology, which means that everything that we developed can be easily adopted by industrial players. As we already validated our improvements on an industrial platform at industrial scale on cell level and stack level, means that this is actually also our developments are compatible with the industrial platforms. And we can also employ our achievements both individually. If an industrial player just wants to exchange or modify one electrode, this can be done, but it's also possible to integrate several improvements like on both electrodes and a barrier layer, etc. In that way, it is very flexible to be taken over by industry, and we believe it's a kind of maybe not plug and play, but what we have achieved is on a stage that it can be taken over by industry, partly the ones that were partners in our project, but it's of course open to every industry in the solid oxide technology area. And I would be happy to tell you more about this at our booth, as you can see here in this hall F43. And I'm also happy to answer any questions if there are. Thank you.
Thank you, Professor. So please, if you have any questions from the audience, raise your hand, and I will come to you with the microphone. Yes, please.
Thank you very much for this very interesting presentation. I was wondering what would be the step forward of this project. Do you want to keep on working on this project? And
so what are the next steps in the project?
Yeah, the next steps, like as the nature of the projects is typically they finish. EU has an innovation platform where we have put forward our developments. They are in that way accessible to everybody in the area or to every interested player. And it's now our role to distribute the knowledge and to spread the knowledge, like in this exhibition or here, to make it accessible to potential users. The project itself is of course ending. Some elements will be carried further in forthcoming projects.
All right, thank you. Any other questions from the audience? I have one more question then. So why is it so important that we develop this solid oxide fuel cell technology further? Can you please elaborate a little bit?
Yeah, the solid oxide, both fuel cell and electrolyzer technology, have very high efficiencies. At system level, in fuel cell systems, more than 60% electrical efficiency were demonstrated, and then total efficiency, heat and electricity, we are over 90%. In electrolyzer mode, we are at 90% at system level. And when we talk about electrolysis, we talk about power to X, which is a very hot topic and needed for securing energy supply. And there, this is a big point and advantage of this type of technology. In addition, that they can operate reversibly, so we can, if we like, in a specific application, produce electricity when needed, or store electricity when needed with the same device, if that might be an advantage at that point. Yeah.
Thank you. I think that's a very good call to develop solid oxide further. Please give a round of applause for Dr. Anke Hagen.